Everybody, welcome back to another fun and exciting geometry class. Today we will be getting into lessons 5.5 and 5.6, and that's on page 243. We'll be talking about the area of a trapezoid first, and then we're just going to do some problems and kind of talk about like how you would solve these and some of the logic behind some of the problems. So, all right, area of a trapezoid. So, what is a trapezoid? A trapezoid is a figure that has a base and then a second base at a different length. Okay, so the top is a different length than the bottom, and then the sides are both different. So um, one could actually be straight, and then one could be slanted, or they both could be slanted. So kind of a little bit different type of a figure here. Theorem 71 says the area of a trapezoid is equal to half the product of its altitude and the sum of its bases. So what does that look like? That looks like this right here. So here's the area formula for a trapezoid. You have TR, okay, trapezoid, and then you have the H right there. That's the height or the altitude. And then it says that it's the product of the altitude. So that means we're going to multiply right here and the sum of its bases. So in other words, remember, it's got a different size top than a bottom. So look here. This top is a little bit shorter than this bottom leg. So these two bases are different sizes. So because of that, what we're going to have to do is we're going to have to count them up separately. We can't count them together. We can't multiply them by 2 or something like that. So what we're going to do is we're going to take the height, the altitude, and then we're going to take both bases, and we're going to divide that all by 2. So we're going to just kind of plug in and work this formula. We'll do one of these in just a second, but I just kind of wanted to go over that with you real quick. And then let's talk about this corollary, and then we'll go ahead and do one of these problems. Corollary 71.1 says the area of a trapezoid is equal to the product of its altitude and its median. So this is kind of like a secondary formula that you can use. So let's talk about what this means. The area of a trapezoid is equal to the product of the altitude and its median. What's the median? Well, here's the median, right? In this trapezoid here, this would be the altitude, right? The distance from the top to the bottom. So what does it mean when it says it's median? So that's what it means when it says altitude, obviously the distance from the top to the bottom. What does it mean when it says the median? What you would do is you would take a point here on this middle, we'll call this A, B, C, and D. So you take a point, the median point here between A and B. Then you take the middle point here between C and D. And this line that's created, I'll put this in here as a dotted line. So this dotted line that's created right here, that is going to be the median of the trapezoid. So what it says is we can take the area of the trapezoid is equal to the product of its altitude and its median. So what you would do is you would take, like, let's say this is 7, and this is 20, for example. You would just take those and multiply those together. Now, let's talk about, real quick, let's just kind of tie some loose ends together here about these formulas. Why does it seem like we're using the same formula as a triangle? Because this is really close to the formula of a triangle. Well, the reason being, and let me move this up for just a second, kind of get it out of our way, so that you can see this. If we take and if we extend these lines up and just keep going with this, and we keep going with this line, okay, look what happens. What we end up with is we end up with a triangle. So look at this big triangle that we've created right here, okay? And what you end up doing is you're actually doing a triangle area, except for obviously you're not doing this top part. But the trapezoid is it's like half of a triangle. So that's why it kind of looks the same as the triangle formula right there. So make sure you remember the height times the base 1 plus base 2 divided by 2 will give you the area of the trapezoid. Also, the area of the trapezoid can be done through the product of its altitude and its median. So you could actually do TR equals the height or its altitude times the median, if you have the median or if you can find the median. That's one way to do it. So in this case, we could do this if we had, let's say, if we had the two slant heights. If we had this was 6 and this was 10, let's just say. Well, the median is going to be here. So if we could find this line right here, basically, then we could figure out what that is. And there's some ways, maybe the problem gives you that, or there's some ways that you can figure that out. All right, let's do one of these. Let's use the theorem to solve this. The area of the trapezoid is 55 square inches. The bases are 14 inches and 8 inches. Find the altitude. So one thing that you might want to do is just kind of like draw your trapezoid over here, just whatever. You can draw it however you want to. It doesn't really tell us how to draw it. So maybe just to visualize it, that will help you. One is 14 and one is 8. I would just plug it into my formula. So the area is 55. So that would be the TR, right? Going back to the formula, the TR, okay, is the area. So the area in this one is 55 equals, and then it was the height. That's what we're looking for. So we could actually call this x, because that's what we're searching for here, is that x. And then it's going to be 14 plus 8, and then we're going to divide that by 2. Okay. And then we just need to solve for x. Remember our algebra? So we're just going to work our algebra here, and we're going to try to make this happen. So you can actually divide this out at any point, but you could do that. 14 plus 8 is going to give you 22. 22 divided by 2 is going to be 11. So we'll get 55 equals 11x. We're going to divide both sides by 11, and we're going to get x equals 5. So our altitude here is going to be 5 of this trapezoid. So fairly simple. If you're missing a piece, just go ahead and plug in, solve for that piece, use your algebra, and get the correct answer. Okay, exercise 5.6. This is on the next page in your books. This is on page 244, so you can go ahead and turn there. This lesson doesn't have anything for me to really teach. It's just kind of doing these and practicing these. So what it says is question number 1. Now, I wanted to show you something before we really get into it. Notice next to question number 1 in your book, it has this asterisk. What in the world is that? Why is that there? The reason it's there is because if you go back in the book, like to where they first started doing these, I think it's chapter 2 is where they first introduced this. They say that these problems with the asterisk, they are very important because they're actually used in the future. You have to, basically, they're like building blocks. So in a way, I don't love that the book does this, because it's like you have to solve it in order to use it in the future, but they do. And so we have to kind of, every time you come to these problems, these ones are important. Not saying that the other ones aren't, but these ones with that asterisk out front, they are important. So how are we going to prove that the area of a right triangle is equal to 1/2 the product of its two legs? If you're paying attention, then that is the area formula for a triangle, right? So they're basically saying, let's prove this with a right triangle. So here's a right triangle. Obviously, here you have a right angle. It can't be a right triangle without a right angle. So there's a 90-degree angle. And then you have your hypotenuse, right? And then you have two legs. This is going to be leg 1. We'll call this one leg 1, and we'll call this one leg 2. Could be either one. Now, I want you to notice something just immediately when you look at this. Leg number 2, we could also call this is the what? When we're talking about triangles, this is the base. Okay? Notice that that one down there is a base. It's sitting on that. Okay? Now, check this out. This is an altitude, right? Why is this an altitude? Because it is a 90-degree angle. It is straight up. Like if we were doing a regular triangle, we would have to draw an altitude like this, which gives us our right angles. So altitudes are based on 90-degree angles. So immediately in a right triangle, we have our altitude and we have our base. So altitude and base, they're already set up. So really what they're trying to get you to do here is they're trying to get you to prove, we can do our little T-proof here. One is obviously the given, and I'm not going to take the time to write the given, but basically just that triangle ABC is right. Okay, I'll just, save a little bit of time there. So ABC, and we'll call this one ABC. So triangle ABC is right. And, they tell you that. That's part of the given. So one thing that I would do is I would kind of think through some of these other things. What makes this a right triangle? What are some things that we know of in the right triangle? I mean, we know that angle C is right. And that would be like definition of a right triangle. Okay? We know that angle C is a right angle. So we could just say that. Another thing that we know is that the legs are perpendicular. This leg and this leg are perpendicular, again, by definition of a right triangle. So you could say that leg 1 and leg 2 are perpendicular. And you would say that because of, again, you could go definition, since you already did definition of a right triangle, you could say definition of perpendicular lines. Okay? Perpendicular lines. And I'm abbreviating and things. I'm trying to make the video go a little faster. So number 4, you're probably going to say something like, what is an altitude? Okay, so if we could say that, an altitude is a right, it basically has to be a perpendicular line, then we can get to the fact that our second leg is an altitude. So you could say that L2, I think it was L2, no, L1 is an altitude. Okay, why is it an altitude? Because of the definition of altitude. You're basically just saying, hey, this is how you define an altitude. An altitude is a perpendicular line, the altitude of a triangle. And then I would say that you could then basically put, for step number 5, something like the triangle formula. So what's the triangle formula? The triangle formula is triangle equals base times height divided by 2. And you could say that by just kind of like saying the area formula, let's say area of a triangle. And so there you go. Basically, you're saying that since it's a right triangle, then this is a base and this is a height. That's all you would have to say in that proof there. So kind of prove that the area of a right triangle is equal to 1/2 the length product of the two legs. Basically, by saying that one leg is a base and one leg is a height, you are saying that the right triangle fits into the formula, and it fits into the formula by just you don't have to find the altitude of a right triangle. You already have it. It's given to you because one leg is the altitude. All right, the next one is number 6 that I kind of wanted to show you real quick. So with number 6, prove that 2 diagonals of a parallelogram divide the parallelogram into 4 equal parts. So if we have our parallelogram here, I guess I'll actually draw it. I'll try to draw it a little bit better than that. That's not a whole lot better, but it's a little bit better. So A, B, C, D, you can kind of name it however you want to. And it says here in the given that we're dealing with the diagonals of this thing. So you could actually kind of throw in the diagonals right here. You could say that, that's one diagonal and that's the other diagonal right there. Now, a lot of times in geometry, when we're doing our T-proof, what we have is we're just trying to prove the obvious. And sometimes that's what annoys students about proofs, because they're all like, of course that's true. Yeah, of course it's true. But you have to prove that it's true. You have to tell us why it's true. So one thing that you really need to do with this is you got to flip a lot of pages in your book. And you have to find old theorems and old corollaries and old definitions that you've already had. So in this case, we are trying to say that the two diagonals, okay, so this diagonal and this diagonal, actually divide the parallelogram into four equal parts. So in other words, this part equals this part equals this part equals this part. Now, what does that mean when it says equal parts? Well, remember when we talked about um, area, it was equal meant that it had the same area. So if we can prove that those four pieces have the same area, then we can prove that they are equal triangles or equal parts. Because look, I mean, these are all triangles, right? So that's what we're trying to prove. We're trying to prove that the area is equal. All right, so I would go about this basically by saying, first of all, we're just going to put the given that it's a parallelogram and that the diagonals, and so we'll just write given. And that's in your book. They basically tell you what the given is. I'm not going to take the time to write it out. Step number 2. I think what you're going to want to do here is basically say that these divide the parallelogram in half. In other words, this piece matches this piece. And how do we know that? Well, if you'll go back in your book, and I'll give you time, you can pause the video, go back in your book and look at theorem number 21. I'll write it here as you're looking at it. So theorem number 21, back in your book, here's basically what that theorem says. That theorem says, theorem 21, I'm looking at it right now, that's on page 95. It says that in the opposite sides of a quadrilateral are equal, then the figure is a parallelogram. So if they're telling you it's a parallelogram, then what they're saying is that these diagonals create equal pieces. Okay? So theorem 21 it's actually the converse of theorem 21 that you could use there, and you might want to write converse next to it. Sorry, too many C's. Converse, right there, something like that, to say that, you're using the converse of theorem 21. But basically, you're going to say that, and you could call it ADB or ABD. So you're saying that triangle ABD is equal to or congruent to, you could really use probably either one there, because the area is equal. We haven't really proved that yet, so I guess we could use the word congruent there probably first, since we haven't proved area. And then BCD, so triangle BCD, we could say that those two are congruent based on theorem number 21. The next thing that I think the next place that I would probably go with that is, now that we have that these are congruent, okay? So basically those two things are congruent, and then you would prove that these two things are congruent. So you could do both sets of angles really with that, both sets of triangles there, okay? So this one, okay? And you could do this one. You could go either direction there. You don't have to prove them both. You just have to prove one of them, but you could prove both of them separately. That would be fine. I think now what I would do, we could put like O here in the middle, so we'll call that point O. But we could say that DO equals BO, okay, and AO equals CO. How do we do that? Again, this is way back. This is several lessons ago, and this is theorem number 23. So in your books, look at theorem number 23, and that's on page 96. So just turn the page once. And it says that if the diagonals in the quadrilateral bisect each other, the figure is a parallelogram. So we already know that it's a parallelogram, so we just need to say that they do bisect each other. So you could say here for 3, theorem 23, and that's technically the converse again of that theorem. We're kind of taking the backwards approach to that theorem. And we could say that all of those are equal. So AO equals CO and DO equals BO. Okay, So we're saying that all of these pieces are equal right here. The reason for that is by that, or you could also write definition of bisector. Okay, so you're defining that by the fact that they do bisect each other. Then you could do some other things here. Basically, you have that this equals this, right? And that this equals this. We could put 3 over here. And that's because it's a parallelogram. That's kind of part of the given. That probably should have just been done in the given part. And then once you get all of those pieces equal, you could talk about the fact that this, these triangles here are cut by equal pieces, right? So this is going to be like a median. These pieces are going to be medians of this triangle. And then you could do some substitution in there. I'm trying to make the video a little bit shorter, but basically you could do some substitution in there. You could talk about all kinds of different things. Here's what you need to do by the end of this proof. You need to make sure that you have all of these pieces are equal to all of the other pieces, and that the area of those triangles are all the same. That's what you're going for. So hopefully that helps you just a little bit there. I know I tried to rush through that last one trying to get the video done, but hopefully that kind of connected some dots for you, at least gave you a start on that one. I maybe didn't finish it for you, but you can go ahead and continue to work through that, think through that, use your logical abilities there to get to the fact that those are indeed all equal, and they are all, the area is all equal of those triangles in that parallelogram. So, all right, if you missed anything there, obviously slide it back, take a look at it again, and that's all I've got for you. Have a good one. See you later. Bye-bye.